Okay, so welcome everyone to our paper session 28 on robots. My name is Alejandro Martin Gomez from the University of Arkansas, and I will be your session chair for today. So today we have 4 presentations. Each of the presenters will have 12 minutes plus an additional 3 minutes for Q&A. And today we will start our session with Jin-Ha Yoon from the University of Bath in the United Kingdom. And she will be presenting her paper entitled The AI of the Beholder, Experience of Healthcare AI Robots is shaped by user-centered factors, not their visual appearance. So let's welcome our first speaker.
Cool. Hello, my name is Jinha, and I'm presenting our work on the AI of the beholder. Experience of healthcare AI robots is shaped by user-centered factors, not their visual appearance. This work was done in collaboration with my colleagues back at University of Bath. So with demand of healthcare services far outpacing resource availabilities, AI-enabled technologies may pose viable solutions to alleviate this shortage. So recent advances in robotics and AI have enabled a new generation of healthcare AI robots capable of autonomous diagnosis and treatment with high accuracy, potentially improving medical accessibility. But successful deployment depends on appropriate trust calibration. So under-trust in these systems may lead to treatment rejection, whereas over-trust can cause blind acceptance of potentially erroneous decisions. Yet, we don't understand how patients actually develop trust in healthcare AI robots within a realistic medical setting. So, previous research used static images or videos to present such AI robots, but failed to capture the vulnerability and emotional intensity of real healthcare encounters. And trust frameworks distinguish 3 main factors that contribute to trust development and calibration. So first, situational characteristics, or the environmental context in which the interaction occurs in. In healthcare, this is critical because patients experience vulnerability and risk. Second is the robotic characteristics, or the features of the robotic system itself, such as human-like visual appearance or competence in diagnosis or treatment planning. And finally, user characteristics, or the individual differences that the users bring into the interaction. So this can include personality traits or attitudes toward AI technologies in general. And to understand how these factors shape trust, we must study how patients interact with such healthcare AI robots in an ecologically valid scenario that evoke genuine medical vulnerability. Which leads to our research questions. What is the impact of situational, robot, and user characteristics on patient trust in healthcare AI robots? And how does trust in healthcare AI robots influence treatment acceptance and usage intentions? So, like I said before, previous research using images or videos to present AI robots failed to evoke emotional vulnerability that patients experience during medical encounters. Ideally, we'd study real patients interacting with healthcare AI robots in actual medical settings. But the cost and ethical risks makes this infeasible. So our solution was to use immersive VR as it allows us to create the ecologically valid medical scenarios that evoke vulnerability and uncertainty while maintaining experimental control and participant safety. So we conducted 2 user studies to answer our research questions. In the first study, we had 2 main objectives. So first was to validate our visual appearance manipulation of the healthcare AI robot and test whether presentation medium affects perceived anthropomorphism and trust. In this study, participants passively observed robots in a basic general practitioner's office with no healthcare narrative or no interactions. And our first factor was the presentation medium. So we compared the 2 most common approaches which used in previous research, which were still images and videos, and we compared them to our solution, which was VR. Our second factor was the visual appearance, where the low level was a medical robot with a screen display. The medium level was a robot with an animated face, and the highest level was a humanoid doctor avatar. So study 1 yielded two key results. As we increased human-like features from low to medium to high, participants' ratings of trust and anthropomorphism increased correspondingly. This validated that our manipulation was working as intended. Presentation medium didn't affect these results either, these relationships either. So whether participants saw still images, videos, or experienced the robots in VR, the effects of visual appearance on anthropomorphism and trust remained consistent throughout. This was a crucial validation as it meant we could use VR for enhancing ecological validity without introducing confounding effects on key measures. Moving on to study 2, we used the same three levels of the robot visual appearance in study 1, but now we added a crucial healthcare specific manipulation, which was the diagnosis and treatment severity. So instead of passive observation like in study 1, participants experienced a complete medical consultation as a patient. So we implemented hand tracking where the participants could see a realistic skin rash on their virtual hands. And to build anticipation, the experience in VR started in a medical practice waiting room populated with animated patients, a receptionist, and just typical sounds of a medical practice. Then they were transported into a medical consultation in a general practitioner's office where they received diagnosis and treatment from one of the three AI robots. This is where we introduce our severity manipulation for more contextual cues. So in the low severity condition, the healthcare AI robot diagnosed the rash as a common skin condition and prescribed a topical cream to be applied. In the high severity condition, the same rash was diagnosed as requiring minor surgical intervention, so a small incision that the AI would perform. Now to answer our first research question, Study 2 revealed a clear contrast with Study 1. The appearance effects from Study 1 completely disappeared when patients faced real medical decisions. So introducing more contextual cues in VR essentially overrode the visual cues that seemed so important in previous studies. Only diagnosis severity mattered. So participants were significantly less willing to accept high severity treatments, showing they were genuinely weighing risks and not just responding to social cues. And one explanation for this difference could be due to the stakes associated with each context. So in study 1, which represented a low stakes context, participants were passive observers, comfortably evaluating the robots with no personal consequences. And in these situations, anthropomorphic features capture attention and build trust through social familiarity. But in study 2, which was a higher stakes context, participants experienced genuine medical uncertainty where they had a condition, they needed to get treatment, and had to decide whether to trust the AI robot with their health. So when the stakes are higher, participants began to prioritize whether trusting the medical recommendation can benefit their health. And we conducted further analysis to identify what actually drives trust in healthcare AI robots. So our regression model identifies 6 significant predictors with perceived competence as the strongest predictor. Visual appearance and anthropomorphism were completely excluded from the final model. They simply didn't predict trust in the healthcare context despite the effects in study 1. So our model demonstrates that where stakes are higher and where decisions can have real consequences for well-being, system competence, user attitudes toward AI, personality traits, and perceived risks all mattered more than the human likeness of the healthcare AI robot itself. Now, our second research question examined whether trust translates into real healthcare behaviors. So trust in healthcare AI robot was a strong predictor for both treatment acceptance and future usage intentions. This mirrors what we know from human physician-patient relationships, where trust is fundamental to whether the patient adheres to the treatment. And we also found that diagnosis severity significantly influenced treatment acceptance. participants were much less willing to accept high severity compared to low severity treatments, as people are naturally more cautious with riskier medical procedures, whether recommended by a human doctor or a AI system. Our methodological contribution is as important as our findings. So study 1 validated that VR doesn't distort how people perceive anthropomorphic features. But study 2 revealed VR's unique capability to create the higher stakes context that fundamentally changed our understanding of trust formation. Images and videos keep participants as detached observers in low stakes, while VR transform participants into vulnerable patients. And this higher stakes that participants experience in VR is what eliminated the appearance effects. And simulating interactions with healthcare AI robots within VR is also a cost-effective way of testing before the physical deployment. So our findings point to a crucial insight where in healthcare, when patients truly need medical assistance, the common emphasis on making robots look human-like becomes largely irrelevant. What matters instead is the interplay of context, robots' actual capabilities, and the patient's own characteristics. This means the design of healthcare AI robots must move beyond appearance. What patients need are systems that actually communicate clearly, explaining what it can do and it can't do, and how decisions are made. Only then can trust be calibrated to real performance and not superficial cues. Of course, trust is not built in a single encounter, so our study only provides a early snapshot. But the bigger challenge is now understanding how patients' trust develops and deepens through repeated interactions as these technologies become part of everyday care. So all in all, competence and user-centered factors matter more than the appearance of the robot. And if we let this principle guide how we design, develop, and deploy healthcare AI robots, we have the chance to build systems that can earn trust, deliver genuine value, and ultimately fulfill the promises of healthcare AI robots. And if we don't, we may risk failure, not because the technology lacks potential, but because our priorities were just simply misplaced. Thank you for listening. And I do have a poster up today. So if you have any other questions that you don't want to ask right now, you can come find me later.
Okay, thank you very much. That was just right on time. So we have about 3 minutes for questions. Do we have any questions from the audience? Questions? Well, I might have a couple of questions then. So I wonder if the type of procedure or the action that in this case the robot is performing would affect the trust, right? Because I would assume it will be a very different situation whether the robot or the agent is used for diagnosis or general care as opposed to other procedures that are more invasive, like surgical scenarios, right?
Yeah, exactly. So for this study, we just demonstrate so for this one, we went for the diagnosis of eczema, which isn't exactly a very high stakes medical condition. So we're just trying to demonstrate that for a lower stakes medical condition, this is how it works. And we basically use VR to show that we really need to consider the environment or like the stakes involved within that particular medical condition. So like you said, if it was a different procedure, then definitely we would have found maybe more rejection from the participants because, for example, in our study, we used the high severity treatment as, a surgical incision by a robot, which is quite gnarly to be honest. And so when they heard that, they're like, no, I'm not doing that. So I think we need to do a bit more work on exploring these other, because it's a range of stakes, right? So we need to really demonstrate like all these different types of stakes.
Okay, thank you. Do we have any questions? Okay, there we go.
Hi, thanks for your talk.
Thank you.
I'm curious what the demographics of your study pool were, like age, prior experiences with healthcare, things like that.
Yeah, so we conducted this study at the university. So it does range from all the way from university students who are roughly like starting from 19 to 23. But we also got a bit more. So I don't know if you've been to Bath, but it is quite a senior friendly town, I'd say. And we got really lucky where we were also able to recruit all these like senior participants. And yeah, you can read a bit more about it in our paper where we found that like actually younger people might have much different experience or perception compared to like the older participants.
Thank you.
All right, thank you very much. Just as a reminder, if you have any more questions for our presenters, you can post them on Discord. And with these, we are gonna move to our second presenter. So
this paper is a collaboration between the Coburg University of Applied Sciences, where Stephen Huck and Professor Jens Coburg are from, the University of Cambridge with John Dudley and Per Ola Christensen, and from the University of Birmingham, where Diyar Abdul Karim and myself are coming from. And why is this? Okay, good. So, what are we looking at? We mostly looking at collaboration between humans and robots, where we hope to get the best out of both worlds, the flexibility and understanding of the problem by humans, as well as the accuracy and capability of the robots. And nowhere that shows, that appears more than in ad hoc applications where we don't have initial mapping, we don't know what is the task, and the human is guiding the robot as we go on. So let's say that I have a car shop and I'm raising the motor out of the car, and I decide that I want to do something in there. Maybe I need to weld the point. So I'm the one who's directing the job, but a robot arm in the installation is the one that does it. So let's say that I need to access a point in the engine. It's important that I will understand if robot can do it and what it's about to do. So maybe we envision that the user is wearing an augmented reality display, and by taking the controller, it could guide the robot to a certain point that it needs to reach, and we can visualize the robot arm coming into that point. And once we're happy with it, we can give the command to execute it. However, in some cases, the operation might be more complex that needs to have an access to a line or to an area on the task space. For example, let's say that I want to weld a line across the engine. I need to know that the robot can access each one of points along that line. Current ways of displaying things will ask me to bring the virtual robot to a certain point and check all along the path to see that this is accessible. Now, while I can do that, that might take time and could slow up the design process. So that's what we came out to do, and we look at different ways that people visualize today with robotics, whether it is that we show a robot arm doing several steps along as they do an operation, or another common display is to show the general space that the robot occupies during the operation. That's mostly for safety, so that people will make sure that their arm are not in the robot path. However, both those displays are hard to show details on an area. So we want to reveal the information which is important for the success of the task, in particular the reachability of the head of the robot into all the points along a path and without cluttering the display. So our contribution in this paper were a new visualization technique called ReachVox that shows reachability over a line or an area, and a user study that we did to verify if this indeed is more effective using about 20 participants. So what is ReachVox, or in short for reachable voxels? What we do is to look at an answer for a success of a task per voxel of the task space. So we basically show results over a volume. And the volume is bigger than the actual task space, and there's a reason for that. So we look here, for example, at the top of the engine, and we can see that there's different voxels. Some of them are green, some of them are red. The green are ones where the robot was able to reach that point and did not intersect neither the robot itself nor the engine on the way, while a red point is unreachable by the robot. And the reason that we show such a lot of information is because the user have to get a decision such as, maybe I need to rotate the motor, or making it higher or lower so it will be more accessible to the robot. And we believe that showing a large area of information will have more intuition to the person, not just whether you can do the task at this point, but also where you can rotate to make it better. So, okay. So generating that display of accessing every point is actually quite hard. It's NP hard. And to be able to do that for that user study, we actually constrain what space are we showing. And we did a brute force computation, but obviously for a practical system, this requires a bit more steps, such as computing that in parallel, maybe training a model to estimate such points, or using hierarchy. Okay, so we plan to do a user study where we compare this new visualization method, the ReachVox, with two common displays, which is one, enable the user to hold a virtual robot actuator end effector and move the robot along the task. And another is called ghost robots, where you see multiple points along the line. However, with preliminary testing, we immediately saw that the ghost robots is extremely busy display and basically obfuscate the answer, whether it intersect the target or not. So we decided not to use it at all. We just compared ReachVox to the base. So the task is, I'm going to the car shop and I have a robot that can do the task. I have a crane where I lift the engine out of the car, and that crane I can control going up, down, and rotation. We used about 9 rotations and 4 different heights, so to a total of 36 different positions of the engine. And the user either can use a base method where he go around the engine, and when he wants to see if he can weld along those lines of white points, then he holds the end effector of the robot and try to move and see that he can access every point. Or that we show a volumetric display of accessibility, where most of the effort is not by moving the robot, but rather moving the engine, and see at which point we can get complete access to the line of white points. Okay, so we did the user study. As expected, it show that task completion is much faster using our display. When we say what is the task completion, we ask people to get the engine and to a point where they can say this is where the robot can do the job, or that they fail 8 times, and then they go to the next question. Um, Not just the time completion, also the number of rotation of the engine are lower with our display, which signals that it gives more intuition regarding where to rotate the engine to find the correct orientation and position. We tried it in different difficulties where paths that are in a concave environment are harder for robots to access. And indeed, you can see that it takes more time for concave, but just as well, better visualization makes the job easier. What's even another thing which is important is the perception of the users. They feel that it's easier with this visualization while they try to move the robot, and every time that the virtual robot arm is getting stuck or cannot get to a point, it reduces their trust in the robot. They feel like they're doing a trial and error. And you can also see that in how they perceive the safety around and total trust for the task. Okay, so we obviously saw that our new visualization outperformed previous conditions. And what's important is not just for the time it takes to check in situation, but also to understand it and have a better prediction of where to move the engine to make things better. And while VR display by itself is helping a lot for both on-site and a remote operator, as it gives a better view of the environment, the task, with the robot and other issues. What we saw was the important, and in particular in such a wide display, it's important to focus the attention of the user on things that will affect its success. Okay. This is just one example. We look at that as a way of basically showing volumetric display of task success parameters. Some tasks have different success parameters. For example, if I want to make sure that my welding will be not just accessible, but there will be a short time going between one point and another, it could very well be that a line as I draw to you will be accessible, but somewhere in the middle, the robot has to correct its reach point, and that will cost time. So that could be another parameters to display in the voxels, such as the change between angles as we go from one to another. That could also be part of a success score. And other applications that need to use areas or line could be stretching from painting a continuous layer of material, or even assembling objects. Think of someone who's standing next to a desk and just bringing up objects and ask a robot to assemble them. And as the assembly goes on, the understanding whether a robot can reach a certain point to weld it becomes more and more complex. We have limitations in our implementation. For example, our calculation of the visualization right now was quite naive, just to be able to do the user study. And most of our participants were students, then were very experienced in VR and gaming, but not necessarily in robotics. And it could very well be that people that are very experienced with that will have different feedback, but it does show the ease of getting people that are less experienced into the task. So that's it.
All right, thank you very much. So we should have time for one, maybe two questions. So we have one question over here on the left, and then we have another here.
Thank you very much for interesting insights. With coming from a robotics background, I can guarantee that the study would turn out different with understanding of inverse kinematics. I'm wondering on how fast you can calculate the reach or the voxels within the working space of the robot. Is it in real time, or do you have like to draw the line and then wait for the processing?
So right now, this was so you have basically you have an arm, and each joint could have different ways to move, and we sample each one. So this one took a few minutes, so we did before.
Okay.
But as I said, we didn't invest time in getting that sped up. It could be sped up both by we can easily parallelize that process. We could also use some hierarchy or focus on certain area first and then update the others. And another option, which is very popular today, is to train an approximation for that function using a model.
Mm-hmm. How did you solve the inverse kinematics? Did you use the UR controller, or did you use any open model for the calculation of the possible configuration of the
Maybe
robot?
that seems to be like a longer question. So
Sorry.
just to give opportunity to somebody else before we move on, we can.
Okay, but
discuss
we
that
use
later.
Ross for.
Okay. Okay. Okay, so we might have time just for one very last question.
Thank you for the nice talk. I'm Katie, and I work with robots at hazard environment like particle accelerator, and I wonder, similar in line to this question, what is the differences between the reachability map with the capability map of the robot arm? So the capability map of the robot arm, which depends on degrees of freedom and where it can go, that's the reachability map is combined with the geometry of the environment.
So if I understand what you say, there's many times when you buy a robot, you get a map of where the robot is accessible. But that's take into account only the robot. It doesn't account the objects that you need, the fact that you change the environment by adding more obstacles and so on. What we show is using the scene. So, so while when you buy the robot, you take that into account, and usually in most applications, you have the time to plan the production line and what will happen. We, in particularly looking at things such as ad hoc applications. So we have to take into account the whole environment around that. So
Okay, thank you very much.
Okay, thank you so much.
Yes.
Thank you so much for the introduction. So yeah, I'm going to talk about if we can use XR as an environment to simulate user studies in human-robot interaction. So as most of you might know, in human-computer interaction or human-robot interaction, we do a lot of user studies to find out if systems or interaction concepts do work for the users. In robotics especially, this can be difficult because the robots are expensive, they might not be accessible because they are in the workflows, and also they could be danger issues because it's heavy machines which are dangerous to interact with. So as we also saw in the first paper, XR can be an accessible, inexpensive, and controllable tool to simulate these settings. However, especially in user studies, we need to know if the results are transferable to the real-world counterparts because we want to do the interaction in the real world. So to do so, some studies, as you also saw before, compared the perception, but not so many papers looked into the interaction. So there are a few papers looking into interaction with robots. However, they mostly look into interaction scenarios where there's no contact between the robot and the environment. So there are steering tasks or drone control But interaction with the environment might be very important, because in XR it was shown that the perception of stiffness and pressure might be different than in the real world. So if we use a robot in this scenario, the perception might differ. Also, these contact scenarios are a problem in HRI, or a challenge in general, because if you control or teleoperate the robot, you don't know how big the force at the tip of the robot is. So this is an important issue to research in human-robot interaction, and there are different concepts to address this, such as visualization or automation, and these concepts haven't been compared before. So my thought was, we have this issue in HRI. It would be nice to do the study in XR, but we don't know if the results from XR would translate to the real world. So this is what I wanted to look into. So the first question was, can we use XR to simulate this contact-intensive scenarios? And then in the study, can we look if what concepts can help us to enhance the force perception during these scenarios? For this, I needed an exemplary use case, because of course the participants would have to do a task. So contact-intensive task, what can that be? It can be different tasks in the industry, such as polishing or grinding, or also big application areas, medicine, where you have palpation, suturing, or ultrasound imaging. I decided to use ultrasound imaging because in ultrasound imaging you have a continuous force on a surface, and this force has to be consistent, because we do need some force for having an ultrasound image and a good quality. But if we use too much force, the tissue deforms, and then the image-based measures get different. So if we want to have a repeatability, we need a consistent force. So here you can see the study set up. The top image is the real robot. So you see we have a robot where we attach an ultrasound probe that just does ultrasound imaging. We have a small screen, and here you can also already see the force visualization. And in the lower image, you can see the virtual robot. So we have a replica of the scenario. We used AR, so the desk and the wall are real, but the robot itself is in XR, and we simulated it using ROS, and also we simulated the ultrasound image using a texture-based approach. As I said before, we also wanted to look into this force assistance approaches. So in HRI, how can we support the users if they have to assess the contact force? And one approach that is prominent in the literature is sensory substitution. So we map the haptic perception onto another sensory channel. And which was shown to work good is visual feedback. So we used this bar that you can see beside the ultrasound screen, which changed height and color depending on the force. And we displayed it besides the ultrasound screen, because this was shown to be a good positioning as users look onto the ultrasound screen during the interaction. The second approach was partial automation. So if we want to have a contact force, it really is just movement in one direction. So you just push in the direction of the end effector or the ultrasound probe. This means we have 1 degree of freedom that is responsible for the force, and 5 degrees of freedom that are responsible for the rest movement. So we had it decoupled, so the 5 degrees of freedom could be controlled by the user, and 1 degree of freedom was controlled automatically. To do so, we used a Microsoft HoloLens. As I said before, we used AR, and therefore we needed a registration because we wanted the virtual robot to be at the same position as the real robot for the setups to be identical. And for controlling the robot, we used a gesture-based interaction technique. So users could do relative movement with their hand, and the robot would move accordingly. So we can see that here, the hand in the corner is moved, and the robot moves accordingly. You see the ultrasound image. And yeah, so this is the setup with the real robot. And here you can also see the bar in the virtual setup. If you press, the bar goes higher, you move the hand, the robot moves, and you see an ultrasound image. To evaluate this, we conducted a user study, a within-subject user study with 26 participants. And the task was, as you saw, we did ultrasound imaging. So in this phantom they were imaging, there were 3 spheres inside, and one had a different size than the others. So participants had to explore the surface while holding a constant force and identify which sphere has a different size than the others. And to measure the performance, we looked into task completion time, force deviation, perceived workload, and trust. And additionally, we conducted a semi-structured interview to get more in-depth feedback how it worked for the participants. So the first results, I'm going to start with the sensory substitution. So the bar you saw, here you can see on the left, if we were in manual control, having this bar showing you the force significantly decreased the force deviation. However, you can also see if it was automated, it made no difference. But in general, it's a good finding that when you have the force visualized, you can have a more consistent force. Also, we did find no other significant effects of the force visualization, which also is good, because sometimes having additional feedback slows you down. We didn't observe that, so really it could be a good opportunity. But then again, we see the bars on the right in the automated scenario are way lower than in the other scenario. So what really changes the force deviation is having it automated. The automation also had other positive effects. So for example, we decreased the task completion time, it decreased the workload, and it increased the trust, which was also reflected by the feedback of the participants, who said that it really eased the interaction, and also the increase of trust could be associated with their higher performance, so they trusted the system more because they could achieve what they wanted to. Now to the evaluation environment, which might be the most interesting thing for an XR conference. So here we could see the plot on the left we already saw before, but we also found an interaction effect with the environment. So in the simulated XR scenario, the force deviation was higher than in the real setup. This was explained by the participants as they felt they couldn't assess the force as good in XR. This makes sense because of the visual fidelity. We used AR on the HoloLens, which has computational limitations, so we had no shadows, no deformation, and that's why participants felt it was way harder to see how hard the robot was pressing. And the workload was also higher in the simulated environment, which could be due to the same issue. So they had to put more work into having a consistent force. And this might, again, also have decreased the trust. So this shows we have no absolute validity. So the results aren't exactly the same in the real setup and in the virtual setup. However, when we look at all the significant results I just presented, we see no interaction effects where having a simulated environment changes the ordering of the effect. So that the visualization just helps improving the deviation is consistent in both environments. That the automation helps even more is consistent in both environments. So in previous work, this was termed relative validity, and this is great because it shows that the comparative effects are the same. And in most user studies, we just want to compare some methods and see which method performs better. And our study results indicate that this is possible to do in XR. Of course, our study still has some limitations. So as I said before, one big limitation was the visual fidelity. We chose a rather simple setup with no deformation instead of using video see-through, where we could have had more visual fidelity, because we wanted to take a simple setup and see if it already works with the simple setup. For the relative validity, we saw that it worked. But if you want to work towards absolute validity, it would make sense to look into different fidelity levels and see if the setup gets more realistic. Maybe also the absolute values will be more similar. Then on the technical side, on the robotic side, the force assistance approaches were relatively simple. So in other use cases, you might need more complex approaches. And for the use cases, I only looked into one use case. So if you want to see if really our results are transferable to other use cases, of course, we would have to do new user studies and other use cases. However, to conclude the results regarding the force assistance techniques, we saw that sensory substitution can help to decrease the force deviation. However, if it's possible, we would recommend to just use automation because it reduces the force deviation even further. And additionally, it enables a reduced workload and an increased trust. And now to the XR part, we saw that our XR study didn't allow for absolute validity. However, the relative effects were the same. So this is a promising result to conducting user studies in XR. Future work, as I said before, would be to investigate, for example, the visual fidelity to see if absolute validity is possible. Yeah, with that, I want to conclude my talk. Thank you for your attention. And I also have a poster downstairs. So if you have more complex questions, we can talk at the poster. Thank you.
Thank you very much. So we do have time for a few questions. Are there any questions from the audience?
Thank you for the talk. And my question is that how do you imagine what kind of other visualization metaphors you can use for the future? Just now you mentioned your slide.
For the post-visualization, yeah. So there were some other words that investigated other simple things, just as arrows and bars. And so from these, the arrow works the best. But then again, this only shows you, we wanted to have one specific force, and it only showed you the relation to that level. But we don't include, for example, the stiffness. So it could be if maybe, especially in ultrasound, maybe you are above a bone, then you don't want to press that hard. Or maybe you are in fatty tissue, so you want to press harder. So one thing would be to adapt this force level in the visualization. And another thing, of course, would be, this is one-dimensional, so we only have the force right now, but we could maybe also have a map in 2D to show at different locations. So I think there are different areas where you could improve it. Yeah, sure, like in the different directions, or also like the voxel map we saw, that you see where you could apply which force. Of course, you could do it like more in a spatial manner than what I did now. Thank you.
Do we have any more questions? If not, I will have one or two, considering we have some time. So ultrasound is a somehow complex image technique, right? It's the pressure is not the only thing that it's important for you to get good image quality. So have you considered integrating other type of features, for example, the orientation of the probe? Is that something you have considered? Or are you looking, for example, in a comparison of the image quality depending on the image that you get? Is that something you have explored?
Yeah, so there's a lot of related work looking into this, and also looking into automating the orientation, because you really want to be perpendicular to really have a good imaging quality. And I didn't look into this yet because, as you say, it's very complex. So there are a lot of other areas where you would have to look into. And I think in an optimal way, you would try a lot of automation, how it works in combination with the interaction. So especially the orientation and the imaging quality, because you can take the image and see how the distribution of the brightness is, to see if you really have a good ultrasound image. So of course you should integrate that. This was just like a first try with a very simple setup, but sure, for future work, I think there are a lot of other things where you could compare visualizing some feedback, so saying, please tilt the probe a little bit, and having the automation and see how that compares to each other.
Thank you. If there are no more questions, I will then ask the second question that I had.
Sure.
This will be a simple question. Why did you decide to use hand gestures to control the robot on that video that you showed?
It's a good question. I worked a lot in how to control the robot. And our idea is that hand gestures enables you to be, you don't need to have any device attached to you. You don't need a haptic input device, which takes away room, needs to be sterile. So we looked into hand gestures, and also I did another study where I compared it to many people to hand guiding, so touching the robot. And gestures are more efficient, especially for precise motion. So we really saw good results for hand gesture interaction. So that's why I included it in this study. And also in this study, it was great because there you really have no haptic feedback. So it was like the worst condition to test the haptic perception on.
Thank you very much.
Hello and welcome. My name is Jan, and today I would like to introduce you to RCLL-AR, augmented reality support for understanding autonomous processes in the RoboCup Logistics League. First, I would like to show you an image of what we've built. This is RCLL-AR. It's an augmented reality application that is extending the RoboCup Logistics League. And in order to understand what we wanted to investigate with our application, I would like to briefly introduce you to the RoboCup Logistics League. So the RoboCup Logistics League is an Industry 4.0 simulation where up to 6 robots are moving simultaneously on a game field. 2 teams are opposing each other, the magenta and the cyan team, and their goal is to autonomously produce products like you can see on the top right here. So these are student teams, and the competitions are in public, so spectators can come and look at what the teams are doing, and therefore also a commentator explains what the game is all about and what is happening throughout the game. So just a quick explanation of what are the robots doing there. So one robot is approaching a station, the base station, and is receiving a base. A product consists always of bases up to 3 rings and a cap. Then the robot brings the base to a ring station, up to 3 rings can be mounted on top of it, and a cap is placed at the end. The product is then brought to the delivery station where it gets verified, and if the product was built correctly, the team receives points. The goal is to receive as many points as possible in a given time limit of 20 minutes. So here's an example that we made. Please look at the robot behind. It takes a product now with a ring on top of it, is moving to the cap station in front where the second robot already waits at the output side. So the stations are mounting now the cap, and at the end, the robot will move to the delivery station, finishing the order. At this time, I would like to ask you, do you think you understood what was happening, and did you realize what the second robot was doing at the same time? Okay, I see some clueless faces, and that's actually what was written in an article 2 years ago. So the spectators were not able to understand why the teams were cheering. So effectively, a product was brought to the delivery that was correct, but the spectators just didn't understand what was happening. And that's a really huge issue in this situation. It's a highly complex situation. Many robots are doing tasks at the same time. And with our system, we wanted to support the understanding of the complex autonomous operations using AR. So AR has been proven to be beneficial in fostering communication between humans and robots by overlaying information about robot sensor information and scene understanding. And it's also used in sports to make it more interactive and engaging for the viewer. Maybe some of you know the technology Hawkeye, where the tennis ball trajectory is visualized to making it more attractive to the viewers. There also has been an AR application for the RoboCup as well for another league, for the small size football league. However, this was limited to post-mortem analysis, and we wanted to provide a system that is usable throughout the whole game such that the spectators could benefit from it. So let's come to our visualizations. So first of all, we have the stations with their station label. There's the team outline depending, the colors depending on which team you're looking at, the magenta or the cyan one. We have a gear animation as well, indicating if the machine currently works or not. There's the product progress. This is depending on the station type as well. So in this case, a blue ring is mounted on the red base. A status is placed below the station, indicating the status of the station, and also the input and output is highlighted by several visualizations. Here, last but not least, the fill state indicates how many rings are still in the slides. So therefore, someone could refill and restock the station if it's needed. Coming to the robot augmentation, so the team color is highlighted here as well. And we also implemented a visualization for the robot path that goes to the next destination of the robot. This also can change throughout the planning because some teams might change their behavior throughout unexpected situations. Last but not least, we also have some basic information about the game. So one referee system is giving out the orders to the teams, and those are visualized on the top left here, also split it into the different parts of the assembly such that you can follow it up a bit easier. So here is a video of how this looked like in our main user study. So two robots were driving on the magenta side here, building different products at the same time, doing different tasks while the stations are still working. With that, I would like to come to our first study that we did. So after initial implementation, we did expert interviews with 7 experts of the RoboCup Logistics League. We did semi-structured interviews for 1 to 1.5 hours each, and we wanted to get first feedback on the visualizations and also to find some other pain points that we might have missed. So what were some of the results? So the most important features for the experts, for the novices, would be the product overview, the team outline, the product progress, and the station label. And also the experts agreed that the visualizations would be helpful for novices as well. Then we had another iteration of improvements. So we added some more visualizations. We also excluded some for our main novice user study, where 56 participants took part in. We split those in groups of 6 to 15 people, and there was an AR group and a no AR group in each of the slots. So throughout the slot, 17 minutes of pure gameplay of the league were shown with the augmentations, of course. And we wanted to see how our system has an impact, and if it has an impact on the understanding, and also how the experience was for the spectators here. So how did our study look like? So we had a mixed design study. So we had a no AR group and the AR group on opposite sides, and we only augmented one team. So the magenta stations were visualized with extended with AR, and the sign stations were not. And for our questionnaires, we used the NASA TLX, the system usability scale, and additional subjective questions as well. So please note, the video that you've seen before was actually the same content that the spectators of the AR group can see on the monitor behind. So this was placed directly behind the stations. So coming to some results. So the participants liked our application, and it was perceived as not very complex. And they said that our visualizations were well integrated. What was really interesting for us was the success of the NASA TLX. So the task for them was to follow the game. And therefore, it was really interesting to see that for the AR group, we found some significance that they felt more successful in following the game. And some other results would be that the AR group was a bit challenged initially by the visualizations, but they could better follow up the explanations as the game proceeded. Also, we asked them if the magenta visualizations had an impact, a positive impact on understanding the science team, and also we found some significance in here. Last but not least, we also did an HMD user study. So 27 participants of the novice user study were also doing this. So they had to follow a single robot on their own for 5 to 10 minutes. And we also wanted to receive some additional subjective feedback on the HMD version. So basically, our application is capable of being deployed on the desktop monitor version and on the HMD version without huge additional work. So here's a short video that we took with the Magic Leap 2 throughout our user study. So here you can see the same visualizations again, but now a bit with less speed. The robot is approaching again the station. A base is dispensed. The conveyor belt brings the base to the robot. The robot will grab it and will move around now. Maybe we would wait for the path again to appear. So you can see the path also is changing throughout the planning as well. So coming to some other results as well. So for the HMD, we saw that it was a much better experience than for the monitor version. So we got an SES score for the monitor at around mean 60. For the HMD version, we got the mean of 76, which is a B plus on the Soro-Lewis curve grading scale. However, we got the feedback that a lot of head movement is needed. This is most probably because the field is quite huge, so it's like 14 meters long, so you actually have to move a bit for it to be seen. And also, one comment was that the HMD version is a nice experience, but it might not be that practical for a larger audience. So therefore, the monitor version would perfectly fine show everything without the overhead of moving around as well. So coming to the conclusion, what have we achieved? So we implemented a reliably working AI application for the RoboCup Logistics League. So we had several slots and we had no issue with our application, so no crashes or so. We also found out that experts were very pleased by the system. They also mentioned having benefits from the system as well. So that was also very interesting to see. The participants subjectively felt more successful in following the game, which is also very important when we want to increase the also the experience for the league as well. However, many participants mentioned that they still were overwhelmed by the experience. So even though we reduced the number of robots and the number of stations, they still were overwhelmed. So with this, I would like to finish my presentation. Thank you for your attention, and I would be ready for your questions.
Okay, so we have time for a couple of questions, and I can see we have a couple of.
Hi, Jan. This is really cool work. Thank you for sharing. And I definitely was one of those clueless faces in the beginning. So it strikes me, and I had this question before I saw your last slide, but it strikes me that even with all of the visual cues, you still have so much going on. I think you were describing trajectories and tasks in progress and whatnot. And when you're designing visual haptics, audio cues, it's really important not to kind of overload the users. That can cause cognitive overload. They're not really sure still where they're supposed to be looking at. So I'm curious, like, do you have any like either qualitative feedback or any quantitative comparisons on which types of information were most helpful for users to make sense of what was going on and which ones were less?
So we actually, I have to go back.
And this is like, and then your last slide was like, oh, people still felt overwhelmed.
So we actually asked them what features were helpful for them as well, for the novices. And they said that the station label was really helpful, the input and output of the stations, and the product progress. So where you see what the task of a certain station is, and also the robot path. So we found some significance in those features.
Okay, I mean, it'd be interesting if like maybe the HMD version has a ability to go, you know, and choose what kind of information that you're able. That would be hard, I think, with the screen.
Actually, we have all of the options. Our framework, so our application can do this all. So we can select which one should be activated or not. So there's also the plan that the commentator has a interface, and we implemented that interface. But for a study, it was really hard to limit it such that not everyone is doing so much different stuff that we cannot evaluate properly.
Fair. Makes sense.
Thank you very much. Very interesting work. Congratulations on the outcomes. Dealing with a lot of digital twin applications, did you at a certain point at the interviews figure out if the latency of the superimposition did affect probably the misunderstanding, because there was a lag visible in the content?
So actually that was some kind of subjective feedback that we got, that it was noticeable that sometimes the visualizations lag a bit. That's because there are many points in the whole processing queue that just take some time. Also, like, we received the messages over MQTT from the team server, and we also have to rely on the data that we receive. Also, the robot paths are quite intensive to visualize, therefore, because you have so many points as well that gets transmitted and you have to pass everything and you have so many robots at the same time. So that is definitely a limitation, and I think that we could improve on that, and that would be a good way.
Thanks.